whatever. Okay, good. So the exciting topic today. So today, what I'll talk about is probably the most beautiful algorithm of linear algebra. And I'll also talk to you about the most impactful algorithm of linear algebra. Okay, so if you want to showcase to people how matrices can be used and how linear algebra is beautiful, then this is the way to showcase that. And the method we'll talk about is PageRank, and this is named by a couple of previous Stanford students, and this is all developed here. Okay, so we will start the following. We'll start looking at the web as a graph. Okay, so the idea is that we will take a real system, we'll take the web, and we will represent it as a directed graph. And then we will use the language of graph theory in terms of strongly connected components, and we will design a computational experiment to learn something about the structure of the web. Okay, that's the idea of what we will do. And we will want to conceptualize how does the web look like. And it will have this bow tie structure, like the bow tie you put on your neck. So that's the high-level overview of the lecture today. So the first thing is, the question we want to ask high-level is, how does the web look like at the global level? And when I say web, what do I mean? I mean the network connectivity representation of the web, which means we will have nodes as web pages, and we will have edges as hyperlinks. There is more and more this issue of what a node is. Like in the old days when web was static, we had basically the HTML 1.0. It was very clear what the web is. If you go to my web page, it's a static HTML 1.0, very nice, right? If you go on Google News, Facebooks, and other places, right? It's not that every unique piece of content has a URL, but it's just one URL where every time different content is being shown. So we will kind of ignore this part a bit, and we will focus on static web pages on the web. The other thing we will also kind of ignore is what people call dark matter, which would be inaccessible pages on the web that are behind firewalls, behind passwords, logins, and so on. So these are kind of issues we will ignore. So for us, web will be this set of web pages. There will be links between those web pages, and all these web pages have unique URLs, right? So when I say a page, I mean a unique URL. So the way you could think of this is maybe there are some web pages here, right? And the way we will connect them is that maybe, I teach a class on networks, that's on my website, and I link to this website or this web page that talks about the class. And this thing says, oh, the classes are in the Gates building. They are here in NVIDIA, okay? But there is a link here that points, to the Stanford Computer Science Department, where the computer science department says, we are the computer science department at Stanford University, and then if you click on Stanford, you end up on the Stanford University main web page. That's what we mean to create a graph, right? So all these links, in some sense, are navigational. So this is what we will think of the structure of the web. As I kind of hinted before, today, many links on the web are transactional, which means after you click them, not necessarily, you don't necessarily navigate to a new URL, but you post something, you execute something, you like something, you buy something. And this is a different type of links that we are not considering here. So we are really considering this kind of prehistoric view of what the web is. Okay? And then you can think of the web as this directed graph where there are web pages and web pages point to one another. And essentially, the way you can think of this is these are all the web pages that Google indexes, right? Like if you say today I'm using Google or web search, it's basically able to search over this type of static, unique web pages. And the other thing is, how are these web pages discovered is that you have these web crawlers or web spiders where you start at a couple of websites on the web and then you consume links and do kind of a breadth first search exploration of the web. And this is what Google does every night, basically. Right? So that essentially you go and discover what are web pages on the web. There is no central directory, so you have to do the breadth first search over this graph to identify the pages. And this is the structure of the graph we'll be looking at. There are other examples of information networks that you can think in a similar way. You can take citations between the papers, where every node is a paper, and how these papers link each other. For example, because this graph only, you can only link back in time, this graph should have no loops, right? I write a paper, I cite everyone that was there before me, so when the next paper comes, again, they can cite me and everyone later. So loops shouldn't exist in this graph. This should be a directed acyclic graph. You know, references in encyclopedia is another example of an information network of how concepts relate to each other. Okay? So these are examples of things we will be looking at. Now, going back to our example of the web graph, the question is, how does the web look like? What would be a good map, kind of conceptual picture of the web? And this is research that was done basically 20 years ago. And at that time, this was, I think, done at combination of IBM and Alta Vista. And Alta Vista was search engine we thought is the best thing in the universe and nothing can be better. And then Google came and we saw how much better search can be. But at some point in time, there was Alta Vista and it was absolutely killing it. But it wasn't so good. I don't know if you guys remember. But either way, right? So this is now 20 years old. The question they were asking is this, you know, how is the web organized? And they said, given a node V, what other nodes can we reach from that node V? That was what they were asking themselves. And the question is both, what can we reach going out from V, but also who else can reach this node, this arbitrary node V? So this means we will define two notions, two sets. We will define an in component and an out component. An in component of V are all the nodes W where W can reach node V. And the out component is all the nodes W where V can reach W. Okay? So in our case, if V is this node A, then, for example, the in component is of node A is A itself. It's node B. It's node C. It's node E. And it's node G, right? These are all the nodes where I can get, where I can go from, and I can get back to the node. So that's the in component, because I'm kind of going towards the node. And then what is the out component? If I start here, who do I reach? I can reach D, I can reach B, I can reach F, I can reach C. So that's the out component here, right? These are the two examples. And then that's the first thing, this in and out component. The second thing is that there are two types of directed graphs. And there are directed graphs that are strongly connected, and we already talked about that, which means that any node can reach any other node. So this means that the in component of a given node is the same as the out component of a given node is all the nodes of the network. Right? If I can reach everyone and everyone can reach me, then in and out will be the same. And because I can reach everyone, this should be everyone. Okay? So that's the strongly connected directed graph. And then there is another type of a directed graph that's called directed acyclic graph. Basically, this is a directed graph that has no cycles. So what does it mean, no cycles? You can reach V, then V cannot reach you. Right? So there's always a path, but only path in one way. Right? So this is an example of directed acyclic graph. You can think of it essentially as a graph, almost like, yeah, you can think of it as some kind of generalization of the tree, right? Where any node can go to its parents, but you can never navigate to a child, right? So you can go from E to then B and A, and then to C and D, right? But you see there is no cycles here. I can go one way, I cannot go the other way. Right? But if it would be a cycle, I could just cycle on the cycle. And what is interesting is that any directed graph can be expressed in terms of these two types. What do I mean by that? I mean that in any directed graph, I can take strongly connected components, merge them into supernodes, and then whatever are the connections between the supernodes, that's a DAG. And you can nicely prove this by contradiction, by basically saying if I would merge two strongly connected components, and now there would be paths both ways, then these strongly connected components are not the largest ones, so the entire thing is a strongly connected component. And that's the contradiction. And I have the hidden slide, I think, after this one that gives the proof. Okay? So now the question is, how is the web organized around in terms of these strongly connected components and these directed acyclic graphs? So just to give you an example, right? A strongly connected component is a set of nodes such that every pair of nodes in S can reach each other, and there is no larger set containing S. So it means strongly connected component is as big as it can be, right? Why do I say this? For example, this is the graph I had before, and this is the decomposition of the graph on the strongly connected components, right? And notice that this thing here contains 4 nodes, even though this by itself is already strongly connected, right? Anyone on this cycle can reach each other. But there exists a superset that is still strongly connected, and that's this entire thing, right? So the point is, S is as big as it can be. So these are now strongly connected components. And then the claim is, right, that any directed graph is a directed acyclic graph on its strongly connected components, right? So basically the idea is that strongly connected components partition the nodes of G. That is that each node belongs to exactly one strongly connected component. So this is my graph, and I showed you before what the strongly connected components are. And now the second claim is that if I build a different graph, let's call it G prime, whose nodes are strongly connected components, and there is an edge between the nodes of G prime, if there exists an edge between the corresponding nodes in the strongly connected components, then this G prime is a directed acyclic graph. I think I have an illustration. Here's the illustration, right? This is the graph. Strongly connected components are 1, 2, 3, and the 4th one. So here they are, 1, 2, 3, and the 4th one. And then there is an edge between the strongly connected component E and the middle blob of 4 nodes, because E links to the middle 4 nodes. There is another one from this blob to F, because, again, member of this strongly connected component points to F. Here is the graph. And notice that this graph is acyclic, right? So that is the claim. The claim is I can take any directed graph. If I identify strongly connected components, represent them as nodes, connect strongly connected components if there are edges between the corresponding nodes in the strongly connected components, then this graph will be a DAG. That's the bottom line. Okay? So now that we have this piece of graph theory in our mind, let's start looking at real data. So as I said, this comes from October 1999 from this Alta Vista search engine. And as I said, the way the graph was constructed is that you start with a set of starting points, starting web pages, and then you do a breadth-first search until you cannot visit any new web page. And that means you now did a complete public crawl of the accessible web. And at that point in time, 20 years ago, this was 200 million URLs, 200 million pages, and 1.5 billion links. So this was a massive graph for 20 years ago, right? Like some of you were not even born yet, right? And people were working with 100 million node graphs, right? These are the authors. They just won a big award 2 years ago for a Test of Time award, and they have nice bow ties. But what they were doing was basically saying, let me take this huge graph, let's say that this is now the snapshot of the web, and let me try to understand its structure in terms of how these strongly connected components fit together into a direct acyclic graph. Okay? So there are 2 issues. First is the computational issue. How do I find strongly connected components? That seems very hard. And the observation is that doing this can actually be quite easy, right? So you can take, again, remember we defined this notion out component of a given node V, which is a set of nodes that, that can be reached from V. I show this up here, right? Sorry. Right? So that's up there. And then what is a strongly connected component that node V belongs to? It's simply the intersection of the nodes V can reach and the nodes that can reach V, right? If V can reach me and I can reach V, then I'm in the strongly connected component of V, right? So what's the idea? The idea is if I can do breadth first search, which is doing the out component, and I create another graph, let's call it G prime, which is the same as G, just edge directions are flipped, then I need to do 2 breadth first searches from the node V, take the intersection, and that's my strongly connected component that V belongs to. Okay? So the idea is, imagine I do the breadth first search from here on the reverse graph, I get the in component, and then I also, do the out component. So maybe I show you this on this example. Here's my graph, here's the node of interest. I will first do the outward breadth first search, and I identify the out component. So these are all the nodes that we can reach, right? If I start here, to traverse the edge directions, these are all the nodes I can reach. So that's the out component of node A. Now what I can do is, I can flip directions of all these edges, and I can repeat the breadth first search. Now, because all the edges are flipped, I will identify the in component, right? Imagine I start from here, but I can only traverse the edge if I traverse it in the wrong direction. So I can go to this guy, I can go to that guy, I can then go here, I can go to B, but I cannot go to G because that's the wrong thing, right? So here is now the out component and the in component. Yes?
In practice, how can we be sure that C will be observed? Because we can only flip that edge if we know if C was observed in the first place.
Great. How you say, how would I even crawl? How would my web spider identify this node? Great point. The only way I would identify it is that I would have to have a list. Otherwise, there's no way I could, like a web crawler, like a Google's web crawler could ever discover this guy, unless somebody registers it and says, hey, I exist, because nobody points to it. That's a great point. All right, so what you are asking is a very good question, because now this really means, do we really have a complete graph of the web? And what are we missing? Because we'll be missing a lot of these types of things, right? Good point, right? So now what is a strongly connected component that V is member of? Is just the intersection of these two sets. So here's a strongly connected component that node, in our case, node A is part of. So this is A, B, E, and D, right? So you have these 4 nodes that are strongly connected component that node V belongs to, okay? And it turns out that this is all we need, and to be able to do this computation. And the reason why this is impressive is because these guys had a machine with 16 gigabytes of memory. That's how much your laptop has today. And that was kind of a super huge beefy server they had. Like nobody had such a big machine as they had, but it was your laptop, right? And they were able to analyze this 200 million node graph and do this BFS by fitting the graph in memory and running this 20 years ago on this less than what you have in your laptop today, okay? So here is what they find, right? They would pick a couple of nodes, and they would run the out BFS, and they would run the in BFS. And the first thing they observe is that if you say, I will take some number of starting nodes, and for every starting node, I will ask, how many other nodes do I visit? Okay? And what you notice is either, if you start at, I know, on these nodes, you get stuck very quickly. You visit maybe about 100 nodes, 200, and then you cannot visit anyone else. But if you would start at any of the nodes here, you essentially visit many, many nodes in the graph. Okay? Is it clear what this is trying to say? Let's say I pick 100 different starting nodes. For every starting node, I see how many nodes does BFS visit. And I just sort the starting nodes by the number of nodes the BFS visited. Right? So you see that for about 20%, I cannot visit anyone. For 20 to, let's say, 50, I visit up to 100. And for the other half of the starting nodes, I visit a huge number. Right? This is logarithmic axis. Right? So this is 10x, another 10x, another 10x. Okay? So that's the first observation. I either get stuck immediately quickly, or I visit hundreds of millions of nodes. Okay? That's the first cool, interesting thing. And notice that huge gap, phase transition here. Right? This is empty. Right? You either get stuck here, or you get all the way up there. Like it's a big step, a big jump. Okay? So what did they find out? When they did this, they basically find that this number is 100 million. Right? So what this means that for about half of the nodes, the size of the out component is about 100 million. And the same, this is now for the in component. They find out that the in component is also about 100 million for about half of the nodes, for these guys here, where the BFS explodes. And then they also see if when they take the intersection of this 100 million and this 100 million, they are left with about 56 million nodes. This is the strongly connected component. And basically, based on just this analysis, they come up with a conceptual picture of the web, right? So what do we know? We know that the out component is about 100 million. We know that the in component is about 100 million. And we know that the two components have 56 million in the overlap, right? So this means that you can compose this and say, aha, I have two sets. They are initially 100 million. They have 50 in the overlap. So it means that this together is about 150 million different nodes. And there is another 50 million scattered somewhere. And they conceptualize this in this notion of the bow tie structure of the web, where this is exactly what I showed you, right? This is the 56 million nodes in the strongly connected component. Then here and here are the nodes that this plus this is 100 million, this plus that is 100 million. And then now you are at 144 millions, 150 millions. So you need another 50 million nodes that they call them tendrils that kind of hang off, or tubes, disconnected components, and so on, right? So they come up with this conceptual picture of the web graph, which says, here is the core of the web graph where anyone can reach anyone else. This is a strongly connected component. There is a part of the web graph where you can only kind of get into it, but you cannot get back. There is another part where you can start from get in here, but again, you cannot get back. And then there are some examples of this kind of tendrils, these tentacles that link in and out component, and so on, right? But it's about one quarter, one quarter, one quarter, and another quarter, right? That's what these guys learned by basically running a couple of BFS searches over a giant graph. So it's quite cool. Any questions? Okay, so now we kind of know that web is a bow tie. Okay, so now the question is, could I identify how important are different nodes that are part of this big graph? And we'll talk about this method called PageRank. And this was really the algorithm that made Google search work. So this was one of the foundational patents that led to Google search engine. And you can see the Google server just outside the classroom. I don't know if you noticed it. But there is a Lego server made out of Legos. That's the original Google server that was running in the CS department on the 4th floor in InfoLab in like 96, 97. Okay? So, and the algorithm they developed is called PageRank. So here is how this works, right? So their idea was to say not all pages on the web are equal. And when you run a query, we don't only care to find pages that contain the query words, but we want to identify the most important pages that have the query words. So the question is, how do you rank the pages? And that's why this is called PageRank, because it gives you a ranking of the pages or ranking of the nodes, right? So the idea is, if you have this web graph, you know, is this node more important or that node more important? And how would you decide on importances of the nodes in the graph? So the goal is we want to rank the pages of the web graph based on the link structure of the web graph. And this area that tries to do these kinds of ranking and analyze the structure of the graph, it's called link analysis. And the goal is to identify importance of different nodes in the graph. And we'll talk about this family of methods called PageRank. Then we'll talk about personalized PageRank. And then we'll also talk about random walk with restarts. And we will see that these are just kind of variations of the method. Okay? Here is how we think of this. We think of this as saying links are like votes, right? We will say page is important if it has a lot of links. Then we need to decide, is it incoming or outgoing links, right? So, you know, Stanford.edu can have a lot of inlinks. You know, some unknown guy gets one inlink, for example, if they're lucky, right? So then you could say, okay, I will just do it based on the number of links that the page gets. But then you could say, but not all in links are equal, right? In links from important pages count more, right? And this is now interesting because you say your importance depends on the links you get, and then the importance of someone you link to depends on your own importance. And this is a recursive question, right? Recursive in a sense that my importance depends on who links to me, and someone else's importance depends who links to them, and kind of it's the same thing, right? So we need to resolve this. So I'll get to that. But the idea right now will be that we say links are votes, and links from more important pages make you more important. So it's not only kind of about the number of friends you have, but also how important your friends are. That's one way to say it, right? So the idea is that this link, a vote from a more important page, is worth more. And the idea is the following, that each page will have a number of links, and each page will have an importance. And when page creates outlinks, it will essentially take its importance and it will evenly split it along all the outlinks. So this means if a page I with importance r sub I has d sub I outlinks, then each of the targets gets r sub I divided by d sub I credit or vote from that page I, right? And page J's own importance is simply the sum of the votes on its inlinks, right? So to show you here, right, if I say this node J, let's see, yes, great, right, this node J here, right, it will take 1/3 of the importance from node I. Why 1/3? Because I has 3 outlinks. It will get 1/4 of the importance of K because K has 4 links and 4 outlinks, and it will sum that up, and that's J's own importance. And then it will take its own importance and split it 3 ways to each of the 3 blue outgoing neighbors, right? So the importance of J is a 1/3 of importance of I plus 1/4 of importance of K, and and then similarly, now these guys will each get 1/3 of the J's importance. Okay, and this is how this will work. So basically what we say is, we say page is important if it's pointed to by other important pages. So the way we can now define the rank of a given page J is simply my importance, if I'm J, is a sum over all the nodes I that point to me. I take their importance divided by their out degree and sum it together, right? I see who's a friend of myself. I ask them how important they are, how big out degree they have. I divide, sum it up. That's my own importance, okay? Where d sub I is the out degree of node I. To give you an example, I'll be using this running example from when the web was very young with the 3 websites. And you can guess what they mean, right? The idea here is, right, that each of these guys has an importance, right? Y, A, and M, right? And the importance of Y, for example, it's because Y has a self loop. It will be, and it has 2 outgoing links. Importance of Y is half of its own importance plus half of the importance of node A, because node A has 2 outlinks, right? And for example, node A, its importance is half of the importance of Y coming this way, and then also all the importance of M, because M has only 1 outlink. And then what is the importance of M? Importance of M is half of the importance of A, because A takes its importance and splits it among 2 outgoing connections. Okay? So that's basically it. And now what do you notice? You notice I have 3 equations and 3 unknowns. So I could basically go and solve this system of equations. I could say I need the 4th equation. The 4th equation could be importances summed to 1, and I could do Gaussian elimination and solve this. Even though this sounds like a good idea, it's kind of not a good idea, because this will never scale to billions of pages. So we cannot just say, here's the system of equations, let's solve it. You had a question?
Is Y self-link fair
Excuse me?
Why is self-link fair? Because it would seem that it could accept many in links, but then hog all of its outlinks by making each of its outlinks unimportant by having many self-links.
How to say, nothing in life is fair. Great, but great point, right? Like you are asking a great question. So the way PageRank is defined is the following way. Now, if you are Google, you can say, hey, will people game me? And if you take my winter class 246, we'll talk about how do you game this. And there is an entire industry that is gaming this graph, right? Because being on top of the Google search results can be quite valuable. So there is huge operations on how do you manipulate the graph, how do you create these self-links, how do you create entire, they are called spam farms, entire farms of web pages that kind of funnel their importance to whoever is willing to pay. So it's a great question you are asking. We won't answer, like, take my winter class if you want to understand that. But it's a good point. It's a perfectly valid point. And of course, you need to ask yourself if you say, I'm Google, do I want to now prune, pre-process, clean this graph of this type of spammers who could create 1 million links there, and the PageRank will just get trapped? So this is an awesome question. And I'll return to it even more in a bit. All right, thank you. Good, this is exciting, thank you. So great, how can we think of this? The way we can think of this is that what do we need? We need to take the graph and we'll represent the graph as this matrix M. And we will call this M to be a column stochastic. Why do we say column stochastic? Because if I'm node J and I have 3 outlinks, then I will put 1/3 on every outlink. So this means that every column will have to sum to 1, right? If every entry is 1 over the degree, and 1 over out degree, so the sum will be equal to 1, okay? So if node j links to I, then mij is 1 over the degree of j, okay? And now this page, and we will define this notion of a PageRank vector R, where I have 1 entry, 1 dimension per page, and this entry I of the PageRank vector R is the importance of page I. And as I hinted before, we will require that the importances sum to 1, so that we have a probability distribution over the web pages. You can think of it that way. But just we require importances to sum to 1. Then you can take this definition of PageRank that I gave you before. You can basically take this equation we saw before, and you can rewrite it in terms of this matrix equation, right? You can say the importances of the nodes. If I have the importances of the nodes, if they push this importance 1 step up to its neighbors, I get back the importances, right? And now you guys should be like, I've seen this before, right? We've seen this before when we talked about matrices and eigenvectors and eigenvalues, right? We had this type of recursive equations where the same thing appeared on both ends. And remember, at that time, I had some lambda thingy here, right? I don't have it anymore, because this means that now solution, my PageRank vector, will be the eigenvector that corresponds to the eigenvalue of 1 of this matrix, right? This is a bit of a preview what's happening. That's why I was saying that this is the most beautiful kind of linear algebra algorithm, right? So this is a recursive equation because I have R on both ends. So let me give you an example. Here's again the same graph that I had before. Here are my flow equations. And the way I could write this out is the following. Here is my matrix M. Notice that every column sums to 1, and that the entry is ij is 1 over the out degree of j, right? This is the matrix M. And what do I say? If I now say R equals M times R, here is my R, here is M and R, and you should notice how basically these equations are preserved, right? M equals R1/2. So if I take M and multiply these two things, this is the only term that survives, for example, right? So this is equivalent to that. Here's kind of pictorial example, and I challenge you to find a mistake if you think there is one. But this is that, okay? So pictorially, we have the same thing. Now, let me give you a bit of a explanation or intuition of this, what we call flow-based formulation. And here is the idea. So PageRank equations are very related to this notion of random walks and random surfers on the web, right? So imagine I have a web graph and I have this surfer, right? Surfer surfs the web graph like a surfer surfs the wave, right? But this surfer is a random surfer. So he surfs the graph at random, right? So this means that at any time t, let's say that this surfer is at some page I. And then what will the surfer do? At time t plus 1, the surfer will follow one of the outlinks from this page I selected uniformly at random. Okay, so this is a random surfer. Surfer comes to the node, looks at the outgoing links, picks one at random and makes a step. And then again to a new node, picks one of the outgoing links at random and takes a step. And that's what the surfer does, right? And this surfer is a random surfer, never gets tired, surfs infinitely long this web graph. Basically randomly walks across this web graph. So let's say the following. Let's P sub t, P of t, be a vector whose ith coordinate is a probability that the surfer is at a given page I at some time t, right? So P of t is a probability distribution over pages, right? So now let's ask ourselves, what is P of t plus 1? Right? And P of t plus 1, the way I can think of this is, if at time t the surfer is one of the pages, at the next step, at the next time surfer will take one step. So it means that, for example, the probability that the surfer will be at page I is the probabilities that the surfer was at the pages, the probability that at time t plus 1 surfer is at page j will depend on the probability that the surfer was at time t at the pages I and their out degree, right? So this means that if at time t the surfer was at any of the pages I, the surfer would pick a link at random and make a step, and the question is how likely is the surfer to end up at j, which is basically just it's equal to the probability of the node of the surfer being at any of the pages I, and then what is also the out degree of page I, right? So this equation is that probability at t plus 1 equals my matrix M times the probability vector of where the surfer is at time t. Okay? So that's the important equation, right? Basically, we follow a link uniformly at random, right? So now let's suppose that after some time, this random walk reaches some steady state, which means that the probability distribution at time t is equal to probability distribution at time t plus 1 equals the probability distribution at time t, right? So this is my kind of my equation. I'm saying my probability distribution converged. And this would mean that P of t is what is called stationary distribution of a random walk, right? I converged to some distribution that kind of gets preserved as the random walker makes more steps. Okay? But what's the point? The point is that we said the original vector R satisfies this equation. And now here, I essentially wrote the same equation now again, just I called P of t, and here I called it R. So what this means is that R is a stationary distribution of this random walk. Okay? So what did we say? What we are saying is that if I solve this R equals M times R, then essentially what I'm doing, what the semantics meaning of this vector R is to say, let's take this random surfer, let's let the random surfer walk around infinitely long so that, and then I just ask, what is the probability distribution of where the surfer might be at some time t? And that is what the PageRank is measuring. Please ask me question now. Yes?
This is modeling convergence, basically.
This is what we are, so, yes, this is modeling, it's not modeling, basically, yeah, maybe another way to say is, this is modeling the stationary distribution of this random walker process on the graph, right? So why is this interesting is because we started with these ideas of links as votes. And then I started somewhere very different. I said, let's have this random guy walking the graph. And the point is that if this random walker walks the graph long enough, it will converge to some stationary distribution where the time doesn't really matter anymore, right? The present and the future are the same. So this will converge where it won't be really matter what's the time. The random walker will just kind of spread across the graph, and it won't matter where it started. I'll just kind of know where it might be. Yes?
So it seems like there are some ways that you could initialize PFT such that it wouldn't converge. Like, you put all the mass on one component so that the walker can't escape, right?
Great question. Hold your question. I will get to it in 2 slides. But great question. Yeah, you're right. So the question was that this graph has to have a certain property because this may not converge. That's what you were asking, right? And I'll tell you what the graph needs to be for this to converge. Good point. Okay, anything else? I want to take some questions because this is very important, because it builds kind of this fundamental intuition for this linear algebra we did. So now it's a great time to ask me questions, meditate this slide, things like that. Yes, go ahead.
What if like the person's, or the surfer's preferences change over time? Does this algorithm catch that?
Great. So here the model of the surfer is that the surfer picks a link uniformly at random, right? Takes the outgoing link uniformly at random. The surfer, you could have a model where the surfer picks these links preferentially based on some pre-assigned probabilities. You can have that, and that's an extension of this model. But the beauty here is that this is extremely simple, has this random walker analogy, and at the end boils down to basically finding an eigenvector of a matrix. Right? So you have this kind of links as Swartz intuition, you have this random surfer intuition, and at the end, both are the same. Okay, great. So what did we learn so far? We said that the flow equations can be rewritten as this R equals M times R. We talked that the rank vector, this means that the rank vector is the eigenvector of this stochastic web matrix M. Given the random walk explanation, what this means is that we can start with any vector U. We can start with any distribution where the random walker starts the walk. But if we iterate this thing long enough, right, we take U multiplied by M, we get a new U multiplied by M again, multiplied by M. If we keep multiplying this long enough, we will converge to a given stationary vector. Right? So if I take that R equals M times R, and kind of I unroll that for loop there, then this is what I get. Okay? So this means that this vector R is its limiting distribution is the principal eigenvector of matrix M, which is this PageRank, right? So this means that R is the limit of taking some vector U and then just multiplying it with M long enough, and I will end up with some stationary vector R, right? Which means that basically this will be the case, right? So if I would somehow, let's say, initialize R here, then this is an R, that is an R, that is an R, that is an R, it's an R, right? But because we said that even if I start with something different than R, if I still keep multiplying, I will end up with dr. Okay? So now this means that we can efficiently solve for R. And this method is called power iteration. So let me tell you what power iteration is. Right? So basically, given a graph with n nodes, then all we will do is the following. We will initialize our R0 to be some vector, let's say 1 over n, just uniform. And then we will iterate this R at t plus 1 equals m times R at t. And we'll keep iterating this until we converge. What does it mean we converge? Between the difference between vector at time t plus 1 and vector t is less than epsilon. And in practice, this iteration will converge in about 50, 100, or about 100 iterations, and will be done. Right? So what does this mean? This means that before I said we have these flow equations. Now what I'm saying is you just start with some arbitrary vector R, keep multiplying it with m, keep doing this long enough, and you will converge to the solution, right? So rather than solving a system of equations, we are just iterating this for loop until we converge, and we will have the solution. And we will converge to the principal eigenvector of the matrix M, right? So now this is like even more cool, right? Because now basically we are solving a system of equations by just multiplying some vector with a matrix enough times. And that's even cooler. Yes?
Have we somehow made the assumption that this is irreducible?
We have made a few assumptions that I will clarify. All right? We made the assumption that M is column stochastic. And that's in some sense, so yeah. But I'll come to talk more about what are the assumptions about M. But we made an assumption that it's irreducible, yes. Good, anything else? Yes?
How dependent is this on the initialization?
This should work for any initialization. If M has the right properties, this will always work. You don't need to worry. So people would usually just initialize to be like uniform, as I showed. Okay, let me now tell you a bit more how to solve, right? So we talked about this. We said we can run this R equals M times R, or we run this iteration until we converge. So let me show you whether this will converge, right? Here's my iteration. Here's the graph. Here is matrix M. Here are the equations. Here is how I initialize. And all I will do now, I will take this R. Here it is. Multiply it with M. And I will get a new vector. And I will now take this vector, multiply it with M again. And I'll get a new vector. And I'll take this guy, multiply it with M again. And I'll get a new vector. And if I keep doing, this is what I will converge to, right? These are now my importances. So page Y has importance 6/15. Another page A has importance 6/15. And page M has importance 3/15. Okay? This would be how this would work. So now the question is, right, I showed you an example where everything works perfectly. So now the question is, for general matrices M or for general graphs, does this converge? Does it converge to where we want? And are the results reasonable? So let me now tell you about some corner cases, how this basic idea needs to be fixed. Okay? There are two problems why this won't converge. And that goes to your question, right? So the first thing why this won't converge is these dead ends, right? These are the pages in the out component that you get into, but there's nowhere to go out from, right? And right, what does this mean? If you think of yourself as a random walker, you just came to the end of the cliff. You came to a web page that has no outgoing edges. You don't know what to do. So this means that these dead ends, these web pages without outlinks, they they leak out importance. Basically, the random surfer goes and doesn't know what to do because there's nowhere to go. So that's one problem, pages without any outlinks. There is another problem, which is called spider traps. And these are basically cycles where the random walker gets trapped, right? And this means that eventually the spider trap will absorb all importance. So let me give you an example. Here is a spider trap problem. Imagine I have this graph where there is a self loop in B. And imagine of this random surfer idea, right? A random surfer starts somewhere, but as soon as the random surfer navigates to node B, it gets trapped in the node B all the time. And if I start, for example, if I create a matrix M out of this, and I would do the power iteration, essentially very quickly the thing would converge where B has all the importance and A has no importance. And this is kind of the results we don't want, right? Like this node A still has some importance, even though the random surfer gets trapped in B and never can get out of it. So this is the example of the spider trap. And then this is the example of a dead end. If I now take and create the matrix as I show, and I would start with some starting vector and multiply, you see the random walker starts at A, goes to B, and then there's nowhere to go from B, so all the importance is lost. And this is the importance leaked out of the system, right? So these are the issues where our our method will now fail if there are these types of structures in the graph. So basically, points, nodes that are dead ends, or these types of cycles, traps, where the random walker can get into, but then cannot get out of. Okay? And the question is, how would we solve this? And the way we can solve this is to define this notion of random teleportation, or a random jump. So our random walker will change a bit. So the process for the random walker will change the following. Whenever a random walker makes a step, the walker, the surfer, has two options. The walker will come, flip a coin, and with probability beta, the walker will keep following the links. And with probability 1 minus beta, the walker will jump, will teleport to some other web page, right? And usually, this value of beta is 0.85, right? So basically means about 1 in 5 cases, the random walker will jump, and for the rest of the times, the random walker will follow the links, right? So the way you can think of it, if this was our graph before, now at any node, you can kind of decide to jump. You can just come to the node and say, oh, I won't follow, I'll just teleport, right? Kind of Scotty beam me up type thing, right? So this is what will happen, okay? So how does this, why does this help with spider traps? This is a solution for spider traps because M here is a spider trap. The random walker will be trapped a bit here, but sooner or later the random walker will decide to jump out and will basically be able to drop this cycle here. So that's why teleports solve the spider trap problem. You are no longer trapped in the trap because you can always teleport. So sooner or later the random walker will jump out. And then what is the solution to the dead ends? The solution to the dead ends are also teleports, where basically we say if you come to a dead end, always teleport, right? So the idea is that rather than thinking of this graph like that, we think of it that if I come to M and there's nowhere else to go, I'll just teleport with probability 1. Okay? And why is this important? Because before we were saying that M has to be column stochastic, right? We said it's an adjacency matrix where columns sum to 1, but notice that M has no out degree. So this column does not sum to 1. And that was the violation why power iteration did not work in the dead end problem. So we will now here add 1/3, 1/3, 1/3. So if you come to M, you just jump. Where do you jump? To any of the 3 nodes, each one with equal probability, right? So that's what we did in this case. Okay? So what is the solution to the dead ends and spider traps? Why do teleports solve the problem? As I said, for spider traps by itself are kind of not a problem from the convergence point of view, but they are a problem because PageRank gives us something we don't want, right? It gives us kind of a trivial result that's useless. So solution is we don't want to be stuck in a spider trap, so we will use a teleportation so that after some finite number of steps in the spider trap, we teleport out of it and we solve, we save ourselves, right? That's the spider trap. And then dead ends kind of are a problem. Our method does not converge to the right thing. And the point is that dead ends, if we don't take care of dead ends, the matrix is not column stochastic. So our initial assumptions are not met. So the solution is to make the matrix column stochastics by always teleporting where there is kind of nowhere else to go, right? If I come to a node that has no outlinks, I just teleport myself. All right? These are the 2 important details. So, and this is exactly what Google's PageRank algorithm is. It's basically a random walker with teleports, where the teleports happen with probability 1 if you end up in a dead end. So the process for the random walker is you make a step, with some probability you follow links at random, with the remaining probability you jump. And the way you can write this out is the following. You say importance of node J is, these are now importances of node I, but this only happens with probability beta. So with probability beta, I decide to, the random walker was at any of these guys and decided to make a step. This is the probability that the walker was there. This is 1 over that is probability that my link was chosen. and then they make this step with probability beta. And then what is this last part? It says, but with probability 1 minus beta, the random walker decided to teleport, to jump. What's the probability that they jumped on me, node j? It's 1 over the number of nodes, because we are assuming that the teleportation happens uniformly at random. Okay? So this is now our new PageRank equation, right? We had this part before. Now we multiply it with this probability to actually take a random link. And then this is the probability of not taking a link. And this is basically saying the probability that the random walker will just directly teleport to our node j by itself, right? So this means if a node has no in-links, its importance will be non-zero. This is the importance of a node with no in-links. There's no other way to get to the node than to directly jump to it, right? Where n is the total number of nodes in the graph. Okay? Great. Any note that here in this, I'm assuming there are no dead ends. I'll fix the dead ends a bit later. Okay? Yes?
We talked about after 50 or 100 iterations, it will converge. Wondering, so when the n becomes larger and larger from billion to billion, is that still true?
You are asking how long, as this becomes bigger, as the graph gets bigger, how long does it take? It will take a few tens of iterations. Let me say the following. Usually people would, in practice, you only run this for some number of tens of iterations, because what you really care about is not for every single node for the PageRank score to converge, but you really care about getting the scores of the important guys, right? So still in practice, people would run this a couple of tens of iterations. Like that MapReduce framework, if you guys know, was developed to run this in some sense, right? Or was one of the workloads that led to development of MapReduce. All right, let me now, so this is the equation I had from the previous slide. If we now want to write this in the linear algebra, we have to define this new matrix A that is called the Google matrix. And the Google matrix will be beta times m. This is the m we had before, plus this matrix of random walk destinations, 1 minus beta divided by 1 over m, right? And if I write A in the following way, then now I can rewrite my r equals m times r as r equals a times r, where A is now this matrix, right? So what does this mean? This means that even this random walk with teleportations is still an eigenvector of a different matrix, right? This matrix A that is both the matrix M plus some constant matrix, right? This is what I wanted to say here. And as I said, beta is usually between 0.8 and 0.9. 0.85 is a good number. So let me just show you what I mean, what we just did. We said, here is our graph. Here is our matrix M. Notice that node M is now a spider trap. So this is matrix M. Then here is the random teleport matrix that I have. So my matrix A will be 0.8 times M plus 0.2 times this 1/3 type matrix, right? And if I add the two together, this is my matrix A, right? So what this means is that if I come to a given node, here is how I'm going to leave. This is how I'm going to leave that node, right? With probability 5/7, I will navigate to Y. With probability 5/7, I'll navigate to A, and 1/15 to M. Why is it? Why are things this way? Because, for example, to go to this node, the probability of traversing by link is 0, but I get the random jump part, right? So that's why this will be this way. So this means now, if I take my starting vector and I multiply it with this matrix A, here are the transition probabilities. And if I multiply this, this will converge to the following result, where Y will have the most importance, This is now, I think, M, and this is A. If I, yeah, right? Do people have any questions about this? Yes?
So green denotes the links created by random teleports?
Exactly, right? So what I did is I added these links to denote random teleports. And I randomly teleport with 1 over 15, which is I can jump to any of the 3 nodes, and I will teleport 20% of the time. So it's 1/5 times 1/3, so it's 1/15, right? While here, why is here 7 over 15? This is 1/2 plus 1/15 or whatever, right? Yes?
So it seems like M has still kind of gamed the system a little bit. It's wound up with the most important score by giving itself a self loop. Is that kind of observed? But even though random teleportation stops you from getting completely messed up by people doing spider traps, it's still kind of
good point. So M gamed the system a bit because it almost like acted as a spider trap. That's a good point. So at the level of individual web pages, you could go and remove these self loops, right? So there is a lot of pre-processing that you could do to, like, removing self loops is easy. What is harder is detecting this kind of farm of pages that kind of coherently links to each other with the goal to improve this guy. That's harder to do, but as I said, there are methods to do that as well. All right, so let me now show you how we actually compute this. One thing you should observe is that this is now a dense matrix. So if this is 200 million or a billion pages, then this is a billion times billion, right? So that's a lot of billions. What do we do? Okay, so how do we actually go and compute the PageRank, right? Here's the issue, right? What we want to do, the key is this iteration where I say our previous R times A is our new R, and I want to be able to iterate this as many times as possible. If A and R and R old and R new are small and I can fit them in main memory, then life is good. As I said, if I have, for example, a billion nodes, and let's say I need 4 bytes to save an entry, so I have, I don't know, a short float of 4 bytes, right? Then, you know, and I need the two vectors R new and R old, each one with a billion entries. So just to store R old and R new, I need 8 gigabytes of memory. And now to store the matrix A, I would need 10 to the 18 billion or 10 to the 18 bytes of main memory. That's a lot. That's a billion of billion. I don't even know what kind of gazillion this is, right? But I would need to do that. So I cannot do this, right? So the point is, I cannot even materialize this matrix A. I can have this matrix because it's sparse, right? This will have, in our Alta Vista case, this was 200 times 200, and then it had 1.5 billion non-zeros. If I would do this, you know, a billion is 10 to the 9. Here it would be 200 million, 200 million. So that's 10 to the 8. So this would be 10 to the 16. 10 to the 16 is 10 million billions, right? It's 10 to the 7 times 10 to the 9, right? So it's a lot. I cannot do that, right? So it would be 10 million gigabytes. Yeah, that's about how much memory I would need. 10 million gigabytes. That's a lot. Okay, so maybe that's more memory than it exists on the whole planet. Okay, so what can you do? What can you do is the following. You can rearrange your computation to look like this. Okay, here I skipped a slide, and this will be your homework problem to basically show how you can rearrange this R equals A times R to something, to something that has this type of form, right? So notice that now I say R equals beta times M times R plus some vector. And this is now elegant because M is a sparse matrix. Multiplying it with a scalar is still sparse. So sparse matrix times a vector, that's okay. And then I add some constant. right? So all of a sudden, we saved a lot, right? M is a sparse matrix. Rather than saying I need order n squared amount of memory, if I have 10 links per node on average, I need 10 times n amount of memory to work, or space to work with M. Okay? So this means that because I can rewrite my iteration this way, I can basically distribute R next to the M, and I have this constant term here. I can now iterate this much more efficiently, and I never have to materialize my matrix A. So what does this mean? This means that in each iteration, all I have to do is compute, take the R old, multiply it with M, multiply it with beta to get the R new, and then all I have to do, I have to add this constant value 1 minus beta over n to each entry in R new. And that's essentially all I have to do. There is a note. If M contains dead ends, then some PageRank will leak. So the sum over j of R new will be less than 1. And all I have to do is I have to kind of multiply the vector so that I have to renormalize it so that the components sum to 1. And this is essentially inserting the leaked PageRank due to dead ends, right? So essentially, what does this mean? Is I can just take my matrix M, run it, even don't worry if it's not column stochastic. With every iteration, a bit of PageRank will leak out. I just need to renormalize this so that it sums to 1. And that's essentially inserting the leaked PageRank. And this is the algorithm. Yes? You're not jumping out of happiness. Yes?
How do we quantify the leak amount?
Leaked amount depends on how many dead ends are there. If there are no dead ends, nothing will leak. So you just reinsert it. It's kind of part of the algorithm. It's not, it's mathematically the right thing to do. So this is not a hack or a problem. It's a convenience, right? Because it means you don't even have to pre-process M. You don't have to worry about anything. You just insert what you leaked, and you get the right thing. Yes, Chris.
Are you missing an R at the end of the equation? Should it be that constant 1 minus beta over n and then times R again?
No. I don't need to multiply it. I just add it in, right? I add it to R, right? Basically, I just run this, and then to every entry of R new, I add a little constant term. And this constant term is essentially the probability that the random walker will land at that node, right? So this is the R new will now say, given that the random walker was at R old, how likely is it to visit R new? And then there is another way to revisit R new is to directly jump to it. This is the probability of that happening, right? And that's it. Okay. So this is it. And here is the entire algorithm. It's really 3 lines, right? Where basically this is the iteration. I iterate until there is convergence. I compute the R new by taking R old divided by the degree of node I times beta, and I go from all the nodes I that point to the node J. And by definition, the PageRank of node J is 0 if the in degree of node J is 0. So if there is no way to get into the node. Now, what I have to do is I have to reinsert the leaked PageRank. The way I do that is to say how much does this, what does this R new dash sum up to, and whatever it does not sum up to, I add to every term, right? So S is the sum of the R dash new, and then this is how much is missing to get to 1, and each node gets one unit of that, right? This is inserting the leaked PageRank to get the new thing. And now, you know, the R old becomes R new, and I can go back here to redo it. Yes?
Multiply the vector R new with a certain constant so that it adds up to 1 again, so that we basically give, because here we give constant 1 minus s over n to all the nodes.
Yes.
Do it proportionally, right?
No, why do you do this? Because again, you say, whenever I came to the dead end, I had to teleport. Where do I land? I land with equal probability everywhere. That's how you think of this, right? This is again saying, oh, and now out of the dead end, the random walker landed at your place, right? So that's essentially it. So what this is now trying to do, essentially, this contains two things. It contains the landing at your place because of the 1 minus beta, plus because I got lost in the dead end. So notice that I'm not kind of explicitly accounting for random jumps here. All right, let me give you an example how this would look like. Here is the graph. Numbers sum to 100. Size of the node is proportional to the number, and these are PageRank scores of the nodes in the graph. What do I like? Let's just look at this and see that this makes a lot of sense. For example, node B has very high importance because a lot of nodes point to it. Like these nodes here that nobody points to still have some importance because the random jump can jump to them. Notice, for example, for example, node C gets only one in-link, but it gets it from node B. So node C is also quite important, but less important than B because B gets all these in-links. In some sense, these B and C have a little spider trap going on, if you like to think of it that way, right? So it kind of raises PageRank of them both, right? So for example, node E has a lot of in-links from these small nodes, so its importance is also quite big. Node D is less important than E because E points to it and also to the node B. For example, F has the same importance as D because the only node that points to D and F is node E. So these two guys have the same importance, right? So this makes a lot of sense, right? And then A, because it's pointed by D, it actually has less importance because there's also that link and there is the random jump. Okay, so this is an example how this would give you importances of the nodes on the graph. So let me now show you one application of this, and we'll talk about notion of personalized PageRank, and we'll talk about random walk with restarts. Imagine you have a graph. Imagine you have a graph of computer science conferences and authors, professors who publish at those conferences, and you connect a professor with a conference if the professor publishes at that conference. And then you could want to ask questions like, what is the most related conference to this conference ICDM? Or, you know, what conferences would I recommend this person, Mike Jordan, to publish at, given who they publish at and where other authors publish at, right? So these are the types of questions I would like to answer. And these types of bipartite graphs, they happen a lot in the recommender systems where you have this notion of an item and a user. So this would be user item type graphs. This could be products you are selling, and these are the users who use your website or who have made purchases before. And then you can start asking, what is the most related product to this particular product? Or what products should I recommend to this particular person? And random walks allow you to do this. Let me show you how, right? So the idea is I'll have this bipartite graph of users to items. I will think of items, products on the top, and users at the bottom, right? And in recommender systems, many times I want to ask, how related are two items? How related are two users? For a given user, what items should I recommend, given that the user has already bought certain set of items, right? And this notion of recommendations, it's called collaborative filtering, which means that I want to recommend items to users based on what this user has in common with other users, right? That's kind of the basic intuition. So the question becomes, if I want to find items that are related, I could ask, you know, are items A and A prime more related than B and B prime? How would you compute that, right? And let me just take out the subgraphs of A prime, and B prime. You would say, A and A prime are basically are 2 hops away. There is one user in between, but B and B prime, there's 2 users in between. So A and B should be more related, AA prime is more related than BB prime, right? So you could say, let's use shortest paths. Here's a counterexample where you say, how about now items CC prime? They have two users who, let's say, bought both items, right? So who's now more related, AA prime or CC prime? And because they have more in common, it should be CC prime that are more related than AA prime. But so you could say number of common neighbors is number of common users tells me how related are two items. And here's an example where this doesn't work, right? Imagine the following. Imagine two red users who have both bought D and D prime, but then this user also bought a bunch of other items, and this other user bought a bunch of other items. And now you can say, are D and D prime more related than C and C prime? And we'd like to say that C and C prime are more related than D and D prime because of all this excess noise here, right? And the question is, what kind of graph algorithm would obey these types of intuitions? And it turns out that random walks on graphs, so basically PageRank on graphs, obeys exactly this type of intuition, right? So basically, personalized PageRank, or what is also called topic-specific PageRank, will rank proximity of nodes with regard to the teleport set S, where teleport set is when the random walker decides to teleport, where does the random walker land, right? And this can be a set of nodes, or the teleport set can be an individual node, and then this is called random walk with restart, right? Whenever I teleport to the starting node. So the idea would be, if I want to say what conferences are related to ICDM, I do a random walk starting here, but whenever I decide to teleport, I jump back here, right? And this way, I will identify what conferences and what authors are most visited when random walker starts at ICDM, and that is the answer. So one way how you can implement this would be to basically take this teleport set S, make it into a vector, and then run your power iteration. But it turns out you don't even have to run power iteration. What it turns out is you can do this basically by just simulating the random walk, right? So the idea is that every node will have some importance, and that importance of the nodes get evenly split among all the edges adjacent to that node, and this gets pushed through. So the idea is that we will start with some query set of nodes, and then we will simulate the random walk, where we make a step at random, and for every node we will count how often the random walk visited the node. And as I said, we will also flip the coin with probability alpha. We will restart the walk at one of the query nodes. And the nodes with the highest visit count, those are your recommendations, right? So the idea is the following. You have a query. You will now start the random walk here, literally simulate it, and you will keep the visit count of how often you visited each node. And then you either continue walking or you decide to restart. And you will just keep a counter for every node, how often was this node visited. Here is the pseudocode. It's amazingly simple. And for example, if you would start with this query node, this would be the visit counts, right? So you would say, what are the most related nodes to this node? It would be this particular node and that node. This one has visit count 16. This one has visit count 14, right? And this means that you can now create recommendations very, very quickly. Whoever looks at this, you say, hey, why don't you look at that and that as well? And this is a very simple recommender system to write that works really well in practice and has been deployed many, 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 many times, right? And all you are doing, you have this kind of different users. Let's say they are interested in different topics. You have your products. Users interact with products, and now you are starting to say which products have the most users in common, where the random walk kind of nicely accounts for multiple connections, multiple paths, direct and indirect connections, and also degree of the node, right? If you have a user who who has super high degree, its importance will get split along many different nodes. So to show you an example, right, I said, given my graph, what are the closest conferences to ICDM? I can also ask more complex queries. I can ask, what are closest conference to KDD and ICDM? Right, so I can use multiple starting points to answer the query. And this is essentially what I wanted to say and to summarize. We talked about PageRank, where we have this teleportation, and the teleportation vector is uniform, right? Which means whenever we decide to teleport, we can teleport anywhere in the graph with equal probability. Then you have this notion of topic-specific or personalized PageRank, where the idea is you teleport to some subset of nodes. And then random walk with restarts, its teleportation vector is different. You always teleport to the same starting node. So the teleportation vector looks like this. And the point is, while this one and this one we usually solve with power iteration, random walk with restarts you can just simulate. Like literally, you can simulate the random walker, and that is super fast, super easy, and gives really good results. So with this, I'm done. If anyone has questions, please come talk to me. Thanks a lot.